let's talk about integrating with spherical coordinates. Well, it turns out if we're integrating over region E, the function f of x, y, z, dv, turns out dv is, in cylindrical coordinates, dv is r dr d theta. Well, in spherical coordinates, dv equals, the book shows y, but it's rho squared sine of phi d rho d theta d phi. So that's the conversion there in spherical. The good thing is, rho is just going to range from, a fixed amount, A to B, they usually call it. So how far out you go from your origin there. And of course, d theta, we usually rotate it from alpha to beta, how much it changes in the xy plane, the angle there. And then phi, well, it's also going to range between two angles. And I believe this book calls it C to D. Gamma to delta, I think, in some places. So this integral then, triple integral over region E, fxyz dv. In spherical coordinates, that's the usual order there, so that we go. So phi is C to D, theta is alpha to beta, and rho is from A to B. Now, because of the conversions, we know x is r cosine theta, so that would be rho sine phi cosine theta. Y is r sine theta, so it would be rho sine phi sine of theta. And then z is rho cosine phi. So based on those conversions, convert your f to whatever function that is. And then you have times rho squared sine of phi. Just like in spherical, we add the r with our dr and d theta and all that. D rho, d theta, d phi. That's the order we try to do those. Okay? All right. So it looks pretty bad, but usually it's not too bad. So let's do one here for this. We evaluate the triple integral over region E, 16z dv, where E is the upper half of the sphere x squared plus y squared equals z squared. X squared plus y squared plus z squared equals 1, I should say. Okay. So we've got the upper half of that sphere is what region E is here, and we're going to integrate 16z with respect to it. So, yeah, the hard part here basically is getting our limits for rho and theta and phi. Well, since we're talking about a sphere, you know, x squared plus y squared plus z squared equals 1, that is simply then rho equals 1, isn't it? And so we're integrating over that solid top half of the sphere, and so rho here is going to range from 0 to 1 to the outside of the sphere. Okay, so that one's easy enough, since that's what that is. That's a sphere of radius 1. So rho will go from 0 out to 1. All right, and if you think about it in the xy plane, then we're talking about top half of the sphere, and so theta is going to go all the way around. Theta goes from 0 to 2 pi. And since we're only talking about in the top half here, so we're talking about this doing the top half of the sphere. Yeah, the angles phi here, well, the maximum angle I'm going to get, I'm only going to go to the xy plane, and so that would give my phi the range of 0 to pi over 2, because I'm going from this tip, and then the maximum angle I would get out of that would be down to the xy plane, which would be pi over 2. Nothing below the xy plane. Okay? All right, so that makes our triple integral here. Then what? Well, phi is going from 0 to pi over 2. Theta is going from 0 to 2 pi. And then rho is from 0 to 1. Our function is 16z. Well, we know z is rho cosine phi. And then dv, the conversion is rho squared sine of phi. So we have rho squared sine of phi, and then it's d rho d theta d phi. Okay? All right. So we're integrating rho first, so that would be phi cubed. So that integral, 0 to pi over 2, 0 to 2 pi. The first integral, we got 16 times, will be 1/4 rho to the 4th, right? Because that's rho cubed, so antiderivative is 1/4 rho to the 4th. Times, we got cosine phi sine phi. And that's going from 0 to 1 for rho, d theta d phi. All right, so we plug in the 1 for rho, you got 1. All right, so and that of course reduces to 4. So we got 0 to pi over 2, 0 to 2 pi, and we just have 4. Now, this is cosine, done that a couple of times. Just make that 1/2 sine of 2 phi, if you want to, which helps us out with the 4 there. And yeah, we're left with 2 there. And you might notice here we don't have any thetas, so we could just separate that out. Couldn't we? 0 to pi over 2 sine be 2 sine of phi d phi times the integral 0 to 2 pi that's d phi, and do this one d theta, just 1 d theta. You're right here yet. So it's 2 sine of 2 phi d phi times just the integral. That's just going to be 2 pi, isn't it? We're just doing 1 d theta. 0 to pi over 2, so this would be u is 2 phi, so that'd be a half, so we're just going to have sine of, negative sine of u, so the antiderivative is negative cosine of u, so it'd be negative. The 2's are going to cancel because you have a factor of a half. Anyway, so we're going to use negative cosine of 2 phi from 0 to pi over 2, which makes it, let's see, pi over 2, the cosine of pi over 2, that's 0, minus cosine of 0 is negative 1. Oh, sorry. That's not correct. Okay. All right, so if we plug in pi over 2, we have the cosine of negative the cosine of pi minus negative cosine of 0. So it's plus cosine of 0. Cosine of pi is negative 1, so negative cosine of... Do it over here. Okay. So this would be... cosine of pi is negative 1, so negative cosine of pi would be positive 1, plus positive 1, so we have 2 times 2 pi, which is 4 pi. Okay. All right. Okay, all right, let's see. Do one more here. Triple integral, spherical. Actually, for this one, I'm just going to convert. Let's convert integral 0 to 3. 0 to the square root of 9 minus y squared, square root of x squared plus y squared, to the square root of 18 minus x squared minus y squared, x squared plus y squared plus z squared, dz, dx, dy. Convert that into spherical coordinates. Okay, so what we've got, of course, z here is between these two. So square root of x squared plus y squared to the 18 minus x squared minus y squared. The next is the x, so x is between 0 and the square root of 9 minus y squared. And then y, of course, 0 to 3. All right. So let's look at these two first. This tells me, if you're just looking at in the xy plane here, we're going square root of 9 minus y squared is that. It's the right half of a circle. And since y is only ranging from 0 to 3, we're talking about a quarter circle there. And so what that gives me is the fact that theta here, since theta is the angle in the xy plane, theta has to be between 0 and pi over 2. Okay? All right, now, if we look at the z here, the lower bound of z, we've got the square root of x squared plus y squared. Well, that tells me we're talking about a cone, top half of a cone. So recognize that. And then the upper bound, z equals the square root of 18 minus x squared minus y squared. What about that? Well, if you square both sides, you got z squared equals 18 minus x squared minus y squared, which is x squared plus y squared plus z squared equals 18. And so there we're talking about a sphere, radius square root of 18, centered at the origin. And since we're doing the square root of it, that's the top half of a sphere. And so basically what we're doing, we're integrating over, well, it's the top half of a cone to the top half of a sphere. And so one thing that tells me is my range for my rho. Okay, and so I'm going out to that square root of 18, so that's the top half here. And so rho is going from, my cone is in here, so I'm going to start at 0 and then go out to the sphere there, which is, so that would tell me rho is between 0 and square root of 18, or square root of 3 times the square root of 2. All right. So that leaves us my phi. Okay, well, basically what I've got here is I need to, for phi, I need to know what where the two of these intersect, where the sphere and the cone intersect. So let's solve this equation here. Well, so my phi is where the cone and the sphere intersect. So I've got the cone, you got z equals the square root of x squared plus y squared. And for the sphere, I've got the other version of it, x squared plus y squared plus z squared equals 18. And so here, one thing I could say is that x squared plus y squared equals z squared. And so let's plug that in for x squared plus y squared. Then I'll have basically these two equals z squared. So I've got 2z squared equals 18. So z squared equals 9. So z equals 3. Well, what that helps me with is then the fact that I know that z is rho times the cosine of phi. And I know that phi is square root of 18. Then the cosine of phi would have to be equal to 3 divided by the square root of 18, which is 3 divided by 3 square root of 2, like we said. So that's 1 over the square root of 2. And so phi here, where they intersect, would be the inverse cosine of 1 over square root of 2, which is square root of 2 over 2, which is actually pi over 4. And so phi is going to range from here to pi over 4. Okay, so rho was between 0 and square root of 18, or 3 square root of 2. And then theta was 0 to pi over 2. So this integral, erase everything I'm doing here. So this integral then would be, I'd go, see, we do rho first, so it'll be 0. I mean, phi first, so 0, right in our integrals, 0 to pi over 4. Then we'd have theta from 0 to pi over 2. And then rho is from 0 to 3 squared of 2. X squared plus y squared plus z squared. Well, that's rho squared. And then dz, that's dv. So dv is rho squared sine phi d rho d theta d phi. And then, of course, those two make rho to the fourth, but basically it. Okay.